This video we're going to prove the rational root theorem, and it goes on to say that if we have a polynomial where a sub n is not 0, we don't want a sub n to be 0 and a sub 0 not to be 0. Then we'll talk about what it says here in a moment. But basically, we want to have a polynomial and talk about its roots. Now, let's start the proof. If a sub n is 0, that implies that f of x is equal to a n minus 1, because this first term is 0 times x to the n minus 1 all the way down to a1x plus a0. Okay, we want to know the degree of the polynomial. The degree of f of x, all we can say right now is it's at most a polynomial of less than or equal to n minus 1. Okay, if this coefficient is non-zero, then yeah, it'll be a polynomial of the degree n minus 1. We want to know what the degree of the polynomial is. We don't want to know that it's less than n minus 1. Or if we look up here, we don't want to know that the degree of this polynomial, the degree of f, is less than or equal to n. No, we want to know exactly what it is. Okay, so in order to know the degree of f of x, we need a sub n to be non-zero. Okay, now what happens? So this part is for a sub n to not be 0. What happens if the constant is 0? Then what we get is f of x is a n x to the n plus a n minus 1 x to the n minus 1 all the way down to a1x plus a0, which is 0. Well, we all know you don't have to add 0. Well, there's a minor inconvenience here that we don't want to deal with. Each of these terms have a factor of x. So we can factor out we can factor out an x. N minus 2. All the way down to a1. Okay. Again, we want to just have a polynomial f of x where we can't factor out an x. Just want to have a nice, simple polynomial. In order to not to be able to factor out an x or any power of x, we need one very simple thing. We need a0 to be non-zero. So once the proof started, these two boxed arguments, they're just bookkeeping. A sub n cannot, we don't want a sub n to be 0. We don't want a sub 0 to be 0. Okay. So f of x is a true polynomial of degree n, and the constant is non-zero. Okay, a sub n is not 0, and a sub 0 is not 0. That is, we don't see any roots immediately. If a sub 0 is 0, we know a root. And that root, of course, would be x. We don't want that. Okay. So now, let us look at f of p over q, which is a root. It is a 0. So I'm going to write this down, except instead of x, I'll say x, but instead of x, I'll write p over q. So I'm just reading from here, but instead of x, I'm going to write down p over q in parentheses. So it's an times x to the n plus an minus 1, x to the n minus 1, and so on to a1 times x plus a sub 0. And we know that this is equal to 0. So we're just really gonna look at this for right now. And I'm going to distribute the powers of p to the over q. So we get an p to the q, p to the n over q to the n plus a sub n minus 1, p to the n minus 1 over q to the n minus 1, all the way down to a1 p over q plus a sub 0 equals 0. And now I am going to multiply both sides by q to the n. So, and then distribute the q to the n. So I get an p to the n plus an minus 1 p to the n minus 1 times q up to a sub 1 p q to the n minus 1 plus a0 q to the n, and 0 times q to the n is 0. Now I'm going to solve this last equation for that term. That is, I'm going to bring all of this over to the other side. So I get an p to the n is minus a sub n minus 1 p to the n minus 1 times q, and so on. Now, when it comes to the right-hand side, so I'm not doing anything to the left-hand side, it turns out that each of these terms have a q, at least one q. So I can factor out that q. And I get an minus 1, p to the n minus 1, a1 p q to the n minus 2, plus a sub 0 q to the n minus 1. Clearly, q, right there, that q, divides the right-hand side. Well, since the right-hand side is equal to this, q must divide that. That implies that q divides an p to the n. Let's just say since. Since p over q is in reduced form, we have that p and q have no common factors. But that implies that p to the n and q have no common factors. Okay. But nonetheless, Well, we have that. Okay? PQ divides a sub n times p to the n. Now, since p to the n and q have no common factors, that means that q does not divide p to the n. But, from right here, q must divide a sub n p to the n. Well, if q divides a product of two factors, but it doesn't divide, say, the second factor, then q must divide the first factor. That implies that q divides a sub n, which is really good because that's one of the two things that we wanted to prove. We wanted to prove that q divides a sub n. And we got it. Now what we want to do is prove that p divides a to the n, a sub n. So we'll come back to this equation right here. And I'm just going to remove these boxes and brackets for a moment. Okay, we're going to use that equation. And this time, well, let me first copy it. Oh, this is a given equation. And I guess I didn't copy it right, so I'll just drag it. Okay, so we know that this last equation is true. Okay, we'll keep the box around it. This time, I want to solve for that term. That means everything else, minus 1, everything else goes to the right-hand side. So a sub 0 q to the n is negative an pn an minus 1 pn minus 1q all the way down to a1p q to the n minus 1. Now, so now we're going to reverse the game. Instead of factoring out a q, we're going to factor out a p. So what we have is a sub 0 q to the n is negative p times a sub n p to the n minus 1 plus this piece with our single factor or p factored out, plus this one where we factor out the p. So we get a1 q to the n minus 1. Okay, now I guess I should have made one statement at the very beginning. So let's state that right now. And a sub n all the way down to a sub 0 are non-negative integers. Non-negative integers. You know what? I take that back. They're integers. Right. I'm thinking n can't be negative. The power can't be negative. But these are integers. But some of them have constraints. We already said that an and a sub 0 can't be 0. Okay. So we are here. And I should have said this with the last argument. This is an integer because p is an integer, and if you multiply it by itself n minus 1 times, it's an integer. A sub n is an integer. This is an integer. Same thing here. A sub n minus 1 is an integer. P to the n minus 2. Keep multiplying p n minus 2 times, you get an integer. And we're told that q is an integer, and when you multiply those three integers, you get an integer. Same thing at the end. A sub 1 is an integer, and if we multiply the integer q by itself n minus times, you get an integer. So everything that's underlined is an integer. And when you add many integers, you get an integer. Okay, so and then when you multiply it by p or negative p, you get an integer. The right-hand side is an integer. Okay, but clearly p divides the right-hand side. I mean, let's think about it. If this here is the right-hand side, and what's in this parenthesis is an integer, yeah, when I divide by p, that cancels out, and I get an integer. Negative an p to the n minus 1 plus a1 q to the n minus 1. Sorry, up to that. Basically, I get this with a minus in front. And this is an integer on the right. This here is an integer. That is, p really did divide the right-hand side. But the right-hand side equals the left-hand side. That means that p divides a sub 0 q to the n. But p and q, or p over q, is in reduced form. That means p and q have no common factors. But p and q have no common factors. But that implies that p and q to the n have no common factors. Now, this basically says that p divides evenly into a0 q to the n. Well, you can't reduce that any. You can't reduce that. So what you have to be able to reduce is that. You get r. R is an integer. So when you divide this numerator by p, you get r, which is an integer, times q to the n, which is an integer. You get an integer. That means that p does divide this. Okay, we know that, but what I mean to say is p must divide a sub 0. Okay. So I formally stated this, and I just, okay, well, this implies that p does not divide q to the n. I have a feeling I said a statement like this a moment ago, but I didn't say does not divide. Q does not divide p to the n. Okay. Well, if p divides this product, but it doesn't divide q to the n, then it must divide a sub 0. That implies p divides a sub 0. Now, just want to be crystal clear about this. If you have 15 into 5 times p, and I tell you that this is an integer, this is an integer. Now, it might be that p is 30 and 15 goes into 30 2 times, and the answer is 10. That is a possibility. Another possibility is that 15 does not go into p, but 5 goes into both of these, and so now 1 times p is p. To be an integer, 3 must go into p. What we don't have going on is we don't have this number going into the 5. Okay, that implies this. But that's exactly the second and last thing that we wanted to show. We wanted to show that P divides A sub 0. Now, what does this mean? So, the proof is done. Let me just show what this means. Okay, we know that P over Q is a root in reduced form. Okay, let's state it formally. In reduced form. Okay, and P divides A sub 0, and Q divides A sub n. So, if you have the polynomial a n x to the n all the way down to A sub 0, where P over Q is a root in reduced form, and P must divide A0 and Q must divide AN. Well, P over Q. That's going to mean that P must be a number that goes into A sub 0. P must go into A sub 0, and Q must go into A sub n. Meaning, if you had f of x is, 3x to the 5th plus 2x cubed minus x plus 13. The only possible rational roots. Well, the numerator, P must go into the constant. So P is one of these numbers. 1 goes into 13, 13 goes into 13, negative 1 goes into 13, negative 13 goes into 13. And Q must be in which set? Well, remember that Q goes into the leading coefficient, which is 3. The only numbers that go into 3 are plus minus 1, plus minus 3. Okay, so what might P over Q be? Well, it's a set of fractions where we use one of those numbers for the numerator and one of these 4 numbers for the denominator. Let's use 1 first. I can use 1 over 1. I can use 1 over negative 1. I can use 1 over the same 1 over 3. I can use 1 over negative 3. Well, I'm done with 1. Let's do negative 1 next. I can use negative 1 over 1, negative 1 over negative 1. I can use negative 1 over 3 as a possible root. Negative 1 over 3 can be a possible rational root. Can use negative 1 over negative 3. Now, done with negative 1. Let's look at 13. I can have 13 over plus or minus 1. And I can then have 13 over plus minus 3. 3, negative 3. Then we go to 13. I can divide it by plus or minus 1. And then I can divide the 13 by plus or minus 3. And we can clean this up a little bit. This fraction is 1. This fraction is negative 1. This is 1/3. This is negative 1/3. This is negative 1, which I already have. This is positive 1, which I already have. And this is negative 1/3, which I already have. This is 1/3, which I already have. These two are 13 over 1 and 13 over negative 1, which becomes 13 and negative 13. Okay, and then we have 13 over 3 and 13 over negative 3, which is negative 13 over 3. And then we have 13 over 1, which is 13. 13 over negative 1, which is negative 13. 13 over 3 I already have. This is negative 13 over 3, which I already have. These are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Maybe none of these roots will work. First of all, these are all rational numbers. For example, 13 is 13 over 1. If you can write it as the division of two integers, it's rational. Rational, 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 rational. They're all rational numbers. Those are the only possible rational numbers. Why? Because whatever rational zero you find, whatever rational root you find, P, and let's see where we have it. P must divide the constant. P must divide the constant. And Q must divide their coefficient. Now, if P divides 13, that means P goes into 13 evenly. What are the numbers that go into 13 evenly? The answer is plus minus 1. That gives you 13. Or plus minus 13. Okay, that is what P can equal. And that's exactly what I put here. And when it comes to Q, Q must divide 3. Q must go into 3 evenly. Well, 1 goes into 3 evenly. Plus and minus 1 goes into 3 evenly. And positive 3 goes into 3 evenly. And negative 3 goes in there evenly. So the only values that Q can be are plus minus 1, plus minus 3. I mean, take any one of these four. Negative 3. Yes, negative 3 goes into 3 evenly. Negative 1 time. Just for the record, 2 goes into 3 1.5 or 1.5. No, 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 no. You can't have fractions. You can't have decimals. So this would be no good. Alright, that completes the proof of the rational root theorem test and some examples. Maybe we should say test. Okay, if you like watching mathematical proofs, my advice would be to subscribe to my channel, as this is what we do here. If you like watching mathematical proofs, definitely subscribe here. See you guys in the next video. Thank you.